All right, so if we're doing the four-element problem, what you can see you get out of all these things is the delta of the first element plus the second element plus the third element plus the fourth element. And you can see they're all going to pull out this common term. I'm going to use an Excel spreadsheet just to make my life easier because there's no way I can do all this without making some sort of calculation error. So if you look at this, they're all going to have a PL over ETH, okay, H naught. And then the difference for each one is going to be this, each element here is going to have a 1/4. That's because the actual length is 1/4 as opposed to the 1/2. And then on the bottom, you're going to have this factor times H naught, because the area is actually something times H naught, and that something is what goes here. So there's that, I don't know what to call it, area factor, okay? All right, so that's what goes on. So you sum all these up, multiply it by PL on ET H naught, and that's the deflection. So here's a spreadsheet. It's real simple. That pretty much does that. So here are the four elements. I'm picking the center points. This is really the center point of the element normalized by L. So the first one is halfway down the first element. They're all at the half points. So that's at 0.125. And then this is the half point of the second element, which is 0.25 on top of this, plus another 0.25 gives you the center point of the third element, and then the fourth element. Then this is just using the equation for the height normalized by H naught. All right, so actually I probably should call this H divided by H naught, because that's really what that is. And this is the length of the element divided by the total length. And this is just going to be that term that goes in the sum, right? This is just the term that goes here for each one of these elements. So it's basically the length factor over the height factor, all right? And this is for the first element, the second element, the third element, and the fourth element. And basically these are proportional to the stiffness of the element. You can see obviously the fourth element is much stiffer than the first element because it has a bigger cross-sectional area. When you sum them all up, that's what you get. So that's basically our answer. So if I go down here, this is going to become 0.455 times PL over ETH naught, okay? And then the error we can get off of that is the exact is, let's get this minus the exact is 0.462, okay? And so that gives us an error of 0.5%. So we're down to about 0.5% error right there, okay? So it does better, all right? But actually you do quite well even with just two elements as opposed to one element. In fact, one could come up with a, actually it turns out, I forget exactly where it is, but for a tapered bar, you actually want to use the cross-sectional area at like the 1/3 point or something like that. And it gives you almost the exact results. Okay. All right, the final question, part D, no, I'm sorry, on part C, it wants you to look at the stresses for the four-element model, okay? And it wants you to actually plot those. So let's look at that. If we're looking, this is part C, so it wants to make a plot of, now I'm going to write the stress, I know it's compressional, but I'm going to write it on the positive axis. So here's X, this is 0, this is L, and I'm going to put, well, we can put the negative stress if you want. Okay, so the first one is to do, for the exact case, okay, Oops, let me get rid of this spreadsheet. Okay, for the exact case, we already figured that out to be P over AE, right? We know that the area is a function of x, so this gives me P E H naught T, and let's do the L, so there's the L up there, 1 plus 3x. Okay? So probably would be bad to actually plot this stress normalized by PL on EH naught T, all right? So actually what I'm going to plot on this axis is minus the stress times EH naught T over L, just to normalize it, over PL, okay, PL to normalize it, all right? So what we see here is a rational function at x equal to 0. This evaluates, so what we're actually plotting is 1 over 1 plus 3x, right? That's actually what we're plotting, okay? All right, so at x equal to 0, this has a value of 1. Oh, you know what? And then we should normalize the x too. So x goes to L. You know what? Yeah, it's probably better. Let's keep the L underneath. Yeah, because this is actually let's keep the L underneath here. So we can actually consider this. We can call this. Well, we'll put an over bar on it. It's a normalized dimension, okay? So it goes from 0 to 1. At 1, this corresponds to x equal to L, right? And so this is, we're actually plotting 1 over 3 over bar, okay? So that gives you 1. At 1 here, we get 1/4. So it's about here, 0.25, right? And it's going to have this downward inflection, right? It's going to go this way. I think it actually goes this way. Which way is it going to bend down? Should bend down this way. Let's get a half point. Let's put in a 0.5. So at the half point, 1/2, this will become 1 over 1 plus 3/2. So that's 5/2. That's 2/5. So 2/5 is 0.4, right? Yeah.
And those two are not going to use something?
No.